All right, here we go. So, last time we were talking about, we just kind of barely started section 6.3. We talked about the fundamental theorem of line integrals, which allows us to compute line integrals in certain cases. Now, there is an asterisk on this. And, by the way, with all of the big, what I like to call accumulation theorems, where we're talking about an accumulating quantity, there's always an asterisk of some form or another. Here, the asterisk is that the vector field cannot be just any old random vector field off the street. It's got to be a gradient field specifically. Fundamental theorem of line integrals makes no comment about how to compute line integrals of non-gradient vector fields. Okay, so anyway, that said, if it is a gradient, if your vector field is a gradient, then you can compute with this handy-dandy little formula f of b minus f of a, where f is what I like to call the anti-gradient of the given gradient vector field. Okay. All right. So let's, we talked about, last time we talked about why that's true, and there's a lot to say there. I don't have time to repeat. Let's dive in straight to an example. Here is a vector field. And I want to compute its line integral over this curve. So curve given, vector field given, compute the vector line integral. All right, now I do want to point out one thing before we get into the computation here. Notice in the statement of the question here, it doesn't say anything about, hey, by the way, you should use the fundamental theorem of line integrals. Right? So something y'all should be thinking about, and I'm going to have advice to give on this eventually. We're not really quite ready yet. But in some sense, when it all comes together, this chapter 6 and chapter 7 stuff, I'll have sort of strategies for how to decide which of the many tools at our disposal should I be using to answer a given question. Right? But I just want to point out here that is kind of something that y'all need to start thinking about now. How do I decide which method I should be using? And notice in the statement of this question, it's almost like it's kind of implicitly pushing you in the wrong direction. The statement of the question, after all, describes the curve with a parameterization. It's almost it doesn't ask you to, but it almost like it's vaguely suggesting you should pull back through the parameterization. After all, you have the parameterization. Right? So, tempting, but that's not the best way to solve the problem. More on that diagnosis stuff later. Okay, what we're going to do here is observe that our vector field is a gradient. This is easily confirmed. Just take the gradient of this function x squared, y squared, easy partial derivatives, and sure enough, it is the desired vector field. So, with this anti-gradient noted, I can just plug into the fundamental theorem of line integrals. Just directly plugging in. Now the detail here that I do have to worry about, and let's see here, let me get my highlighting straight here. So this function f is that thing right there. The remaining details, I do need to know what are these points A and B. Right? So, okay, we are going to have to think about that. How am I going to find, for example, how am I going to find A? A is the starting point. So I'm going to take the starting value of t and just plug into the parameterization. That's my A. And then I'm going to take the ending value of t, plug that into the parameterization, and that gives me my ending point of B that I plug in. And then you plug into the anti-gradient function, compute, and out comes your answer. This integral is 0. Everybody good? Notice I didn't have to use the parameterization to speak of. I mean, I needed the endpoints, right? And I didn't have to do any trig. I mean, at a glance, it kind of looked like x and y are both trig functions. That vector field's got a lot of x's and y's in there. You'd think there's going to be a bunch of trig in this problem. Fundamental theorem of line integrals allows us to bypass that completely. Awesome result. Awesome convenience. Okay, how are we doing? Everybody with me? Everybody on board? Okay, here's a seemingly unrelated idea. I say seemingly. So the idea is path independence. I'm going to describe first the what the property of path independence is, I'm going to start by trying to persuade you how implausible it is, how seemingly impossible. Doesn't seem like this should be possible at all. Anyway, here's the innocent observation. If I'm computing a line integral, that line integral is computed over some curve. Stands to reason it would depend on the curve, right? After all, that's, if you think about what a vector line integral is, vector line integrals say I'm going to move literally along the curve, right? In increments. And as I move along the curve, I'm going to compute stuff. So where you are computing the vector field and the dx vector, etc., where you're computing it, surely that should influence what the answer is, right? I mean, it almost seems like a triviality to say this. Amazingly, this is not always true. Amazing. There are some special vector fields called path-independent vector fields. Some vector fields where only the endpoints matter and the curve doesn't matter at all. Shocking, right? It does not seem like this should be the case. Now let me say this precisely, just so we have it down. So what we mean by a vector field being path independent. This vector field is path independent if, whenever you have two curves, C1 and C2, but I need these two curves, C1 and C2, to have the same boundary points. They have to start and end at the same point. So when I say the curve doesn't matter, I'm talking about the middle part of the curve, but I cannot emphasize enough. I do need the starting point to be the same for both curves. I need the ending point to be the same for both curves. That said, there are some vector fields, believe it or not, where as long as the curves have the same starting and ending point, the rest of the curve does not matter. In other words, you get the same answer. Let's see here. Here we go. Get the same answer no matter which curve you pick. So, shocking. Now, again, I like to push the point of view that this is implausible. I'm going to try to persuade you of how implausible this is for dramatic purposes, right? But to be able to appreciate what path independence is really saying by pointing out how, of course, it should never happen. I mean, this seems extremely unlikely. Now here we go. Here's a shared starting point. C1 and C2 have the same starting point. They have the same ending point. And let's think about these curves C1 and C2, starting with C1. As I move along that part of C1, the vector field is 0, so no line integral there. As I move along this second part of the curve, the vector field's pointing straight up. The curve is moving perpendicular to that. The dot product is 0. So altogether, on C1, the integral is clearly 0. I mean, every step along the way, you get 0. Okay, now let's look at the second curve. This second curve, for the first little while, again, moving perpendicular to the vector field. The dot product is 0. I'm not getting any line integral along in there. But on the second part of C2, I'm going in the exact same direction that the vector field is pointing. The vector field is not 0. There's a significant magnitude there, and you're going to have a positive line integral on that second piece. So altogether, on C2, the integral is clearly positive. Now, this is just an easy for example. Look how much trouble I had to go to find a vector field. This is a really easy vector field to write down. It's not hard. And yet, you pick two different curves, even with the same endpoints, starting point and end point, and of course you get different values. You're computing along you're computing this line integral in different places. It's, dare I say, obvious that these will be different. Okay, now hopefully with a comfortable intuition that path independence sounds entirely implausible. Now let me show you a bunch of vector fields that actually are path independent, amazingly. And here we go. It's gradient vector fields. Quick little point of rigor that we don't need to worry about. I'm going to assume everything cites continuous, so I don't want to get bothered by regularity issues. It's not what this course is about. That said, let's look now at gradient fields. So specifically, these vector fields that I'm interested in here are gradients. And I claim that if I have two curves that start at the same point and end at the same point, I claim we're going to get, believe it or not, the same value for the line integral there. And just to flesh that out, again, here's C1, right? Starts and ends at the points A and B. Here's C2, starts and ends at points A and B, same points A and B. How would I go about computing this vector line integral over C1? Well, let's see here. It's a line integral of a gradient. Line integral of a gradient. Fundamental theorem of line integrals applies. I can compute that line integral over gradient with the fundamental theorem of line integrals. Now let's do it for integral over C2. Well, again, this is a gradient, so I can use the fundamental theorem of line integrals. It's still a gradient because it's the exact same vector field. So now I've computed with the fundamental theorem of line integrals both of these vector line integrals, and notice I get the same formula from the fundamental theorem of line integrals because they have the same starting point and ending point. So both of these integrals are equal to the exact same computation on the exact same starting point and the exact same ending point. So that's why they're equal. And so therefore, these integrals are equal to each other. So we get the desired property no matter what curves you pick, C1 and C2, as long as they start and end at the same A and B respectively. Line integrals will get the same value. What do you think? Everybody all right with that? So to me, this is a tremendous sort of like shock value kind of a thing. I mean, it really seems like, of course, the curve has to matter, right? Look, the curve is where you do the calculation. Of course, it matters, right? And yet, for some magic vector fields, it just doesn't. Thanks to the fundamental theorem of line integrals. Okay, all right. Neat fact. Now, another true fact that's a little bit more trouble to prove, and again, that's just doesn't quite make the cut for things that are worth class time. You're not responsible for this. You don't have to look at it. But this is how the argument would work to justify this second statement I'm going to make, which is that not only is every gradient path independent, but every path independent vector field is also a gradient. So said differently, again, regularity issues aside, we're assuming everything is continuous and differentiable and all that it needs to be. That said, vector fields that are path independent are exactly the same vector fields that are also gradients, and vice versa. Okay. Alrighty. Here's a different way to say it. This is just a rephrase. Let me redraw the picture of path independence. Shared starting point, shared ending point. Here's curve 1. Here's curve 2. Right? Path independence means that these two line integrals are always equal, no matter what two curves those are. Again, as long as you have the same start and end points. Now, innocent observation. Two things being equal is the same as saying that their difference is 0. That's just algebra 1. Now let's think, though, let me color code again. Let's think about what can we say about this difference. That difference. I need to compute a line integral along C1, but then I need to subtract the line integral along C2. Let me say that differently. I need to move along C1, and then I need to go backwards along C2. Let's think about what that curve looks like. That's C1 followed by moving backwards along C2. And notice what it is altogether. This difference is just a line integral on that single closed curve that starts and ends both at that same starting point. So that's the rephrase. Instead of saying that I need Same values for the line integral along all curves that have the same starting point and ending point. Kind of rolls off the tongue just a little bit more easily to say, for every closed curve, see, I should use red here. For every closed curve, I just need the line integral to be 0. That's really a little bit more elegant, a little bit more crisp, you might say. And, pros and cons, there are some situations where the sort of green and blue point of view on path independence is particularly useful, but there are also some situations where this, this closed curve point of view on path independence can also be really useful. Okay, so I'm going to show you an example of the latter now. How this closed curves business is really useful. This, by the way, is a fun example. I think this involves this piece of artwork here. Oh yeah, question.
So are we saying for a closed path-independent curve, their vector line integral is always 0?
Okay, so I'm going to correct your language there. So curves are not path independent. Path independence is a property of a vector field. Right? So let me just rephrase what you said. If you have a path-independent vector field, then on every closed curve, the line integral is 0. Yeah. The closed curve has to be where the vector field's defined. Yeah, I've got to be able to actually compute the line integral. Yeah. Yeah, so I need the vector field to be defined everywhere, and I need the curve to be where I'm going to compute the line integral of that vector field. Yeah. Okay, so nice example that's going to connect up to some M.C. Escher is the artist that drew this. If you've ever seen his art before, you might recognize this one. This is one of his most famous ones, but he's done a bunch of art that is what I call geometric contradictions, like geometric paradoxes, geometric nonsense. So things that look at a quick glance to be physical, but then when you take a closer look, you're like, hey, wait a minute, I'm confused. Wait, what happened? Things that closer inspection, you realize, wait, something's terribly wrong here. Right? So Escher does a lot of that kind of stuff. Okay, so let's get to the example. I'm going to talk here specifically about the steepness vector field. Let's talk about this vector field for a second. It's the gradient of the altitude function. So we've talked in the past about how altitude, right? If you think about the graph of the altitude function, you're basically looking at the hillside or the topography of your landscape, whatever that is. The gradient always points uphill, and furthermore, dot product with the gradient always helps you to compute as you move along a little short piece of path, how much did your altitude increase? So this steepness gradient, altitude gradient vector field keeps track of altitude changes. You might think of it that way. Okay, so what can I say about this vector field? Well, first observation I'll make about it's literally a gradient. You can see it right there in the definition, defined as a gradient. Note, all gradients are path independent. Further note, all path independent vector fields make all closed line integrals 0. Okay. So what? What does this have to do with Escher? Well, let's take a look at what we're adding up in this integral, f dot dx. Keep in mind, f is my steepness vector field. It's my altitude gradient. So f dot dx is supposed to be keeping track of how much altitude changes as I move along the curve. So let's look at this person right here at the bottom of the picture. That person, over the next few steps, what can we say about f dot dx for that person walking along the next few steps? Well, they're going to be moving uphill a little bit. I can see it right there. He's climbing stairs. So f dot dx on this little piece down here is positive. Likewise there, positive. Likewise there, positive, etc. Positive, positive. Notice that everybody's walking up the stairs as I move along the sort of the outside of the stairway here. All these little blue arrows all represent positive changes in altitude. So the way Escher has this drawn, Escher is making it look like all these little blue arrows are uphill, and therefore that the sum of all these f dot dx's, apparently, we're adding up a bunch of positive things. Escher's making it look like this thing's positive. But it can't be. It's a closed line integral of a path-independent vector field. It's clearly zero. So that's the contradiction. So, I mean, the physical intuition is as simple as, you can't walk uphill consistently and get back to exactly the point you were previously. Uphill plus uphill does not add up to level, right? But this is a mathematical way of saying what's equivalent. What do you think? Everybody all right with that? Okay. If you're looking for something interesting to look at, just Google MC Escher. A lot of images come right up. It's great stuff. Okay, moving along. So let's talk about what path independence is good for. I claim path independence is actually really good conceptually for certain purposes. If you want to make sense out of the idea of potential energy in physics / engineering, right? If you want to understand potential energy, ultimately path independence is one of the necessary tools for that. And I'll leave those details for a physics class or an engineering class. So it is a conceptually useful concept, very important. That said, from the point of view of how can I use this to compute stuff, not that much. And let me explain why. It's because if you have a path-independent vector field, we just got through discussing, that means it's a gradient. Well, wait a second. If it's a gradient, I can use the fundamental theorem of line integrals, which is a sledgehammer for vector line integrals. It's really easy to use the fundamental theorem of line integrals. So, who needs path independence as a computational tool? Anytime you could conceivably use it, how about you just use the fundamental theorem of line integrals instead? Right? And a lot of the time, that's a pretty good point. A lot of the time, it's actually easier to just use the fundamental theorem than to execute path independence. That said, there are some cases where the fundamental theorem does not work well. The reasons for this involve the challenges of finding antigradients, which, by the way, I still haven't told you how to do. Let the record show, right? For the moment, I don't know if you all noticed this when we did it, but in this very first example we did here, I just pulled this out of thin air. Right? I gave you no indication of where did I come up with that. I mean, you can easily check that the gradient is what it's supposed to be. But where did I get that x squared, y squared in the first place? So that will come in a little while, later today, fingers crossed. Anyway, there are some cases where finding that antigradient is tough and possibly even intractable. And in those cases, path independence can be a useful tool. Here's an easy example. So here's a vector field. I'm going to take as a given that this is path independent. I'll explain in a couple of minutes how I know that this is path independent. For the moment, let's just take that as a given. I have a curve given. And over that curve, I want to compute a vector line integral of this vector field. How am I going to compute that vector line integral? Now, let's real quick, let's kind of hand wave the obvious solution. The obvious solution here would be to parameterize this curve. X and y are sines and cosines. That means I'm going to have a bunch of sines and cosines in the vector field. My x prime will also be sines and cosines. So when I parameterize and pull back through the parameterization, I'm going to get a bunch of trig integrals. And they're doable, right? But they're half-angle formulas and trig identities, probably a trig substitution or something. It's just a little bit of a pain. Okay, so here's the better move. Far better move. It says right here, my vector field is path independent. Path independent means that as long as I tie down the starting point and ending point, I can trade this curve for any other curve I like. And I tell you what, I don't really like this curve. This is it's a circle. That's where trig comes from, right? I don't like the trigs. I don't like that curve. I would like to get rid of this curve, fooey on this curve. I'm going to throw that away. I'm going to replace this now with any other curve I like. It's got to have the same starting and ending points, which we have noted, right? And so if I wanted to, for whatever reason, I could choose that curve, for example. That'd be weird to choose, but it's legal. I certainly could. What am I realistically going to choose? I'm going to choose the easiest curve I can think of. I want to make my life as simple as possible. Easiest curve I can think of, straight line from A to B. Super easy to parameterize. No trig. Right? You look at our formula here for our parameterization. X and Y are monomials. So these are just polynomials. X prime, again, the derivative of this, polynomials. Right? I'm going to end up with an integral of a polynomial. That's easy. No half-angle formulas, no U subs, just easy calculation. And better than that, notice this. Not only is this easy to parameterize, but notice, and you can see it right here on the picture, for that curve, every point on my newly cleverly chosen curve, every point has y equal to 0. That means that dy is equal to 0. And also, just directly, if y is equal to 0, that makes this whole first coordinate of the vector field 0. Right? So not only does it, in this case, end up that all the trig goes away, but furthermore, I end up with the dot product itself just being flat 0. So this is not just merely an integral of a polynomial. This is an integral of 0. World's easiest integral. Everybody see what happened there? Real slick move. All right. Yes?
Here we didn't use the fundamental theorem of line.
Correct. I did not use the fundamental. Yeah, that's right. So now you bring up a good point, and certainly I could have, right? But technically, I don't know how to find antigradients yet, right? I haven't talked about how to use antigradients, how to find antigradients yet. You might be able to look at this vector field and kind of scheme and strategize and cleverly figure it out in this case. But I want this to be an example of a larger category where sometimes the vector field is worse and sometimes it truly is hard to find the antigradient. Yeah, that's right. Okay. All right. Okay, so how did I know this was path independent? I knew it because of what I like to call this local test. Here's the argument right here. The theorem is going to be, regularity issues aside, a gradient has the property that Green's operator is always 0, and vice versa. If Green's operator is 0, you've got yourself a gradient. So I call this a local test because while the state of being or not being a gradient requires that you have a single function that applies everywhere, the gradient of that one single function has to give you the entire vector field F. So that being a gradient is a global property. But Green's operator is computed one point at a time. Right? Green's operator, it's a formula. And it just needs to equal to 0. Now it's got to equal to 0 everywhere, but the point is the object in question, this is computed 1 point at a time. So this is what I mean by it being a local test. Okay, now how do I know that this works? all of this we already know. We already know that every gradient is path independent. We already know that every path independent vector field is characterized by all closed line integrals being 0. So all this in green we already knew. Okay. Now, let's recall Green's theorem. What does Green's theorem say? Green's theorem says that a closed line integral is computed as a double integral over the interior of Green's operator. So, that integral being 0 is the same as saying that integral's got to be 0. So let me sort of recircle now. Now I know that all 4 of these conditions are all equivalent, because Green's theorem just converts one integral to a different kind of an integral there. Okay, now last thing. Let's look at this condition here. Double integral of Green's operator equals 0. What does this tell me about the integrand? Now let me say it again. What I've got here, this integrand, this thing I have in blue, this function, I need the double integral to be 0. Okay, wait a minute. Slow down. This is for any closed curve. This is for all closed curves. That means that this double integral has to be 0 for all two-dimensional domains. All. That's a lot of two-dimensional domains. How could all of these double integrals be 0? What could this blue function possibly be? So that all the double integrals, no matter what, all the double integrals are always 0. And I propose, and again, regularity issues, but there's really only one reasonable candidate, and that is the 0 function itself, right? If this function were ever non-zero, well, then in that general vicinity, there'd be integrals that are also non-zero. So only the 0 function should have this property. So that then is the final piece of the puzzle. That's why these conditions are equivalent, and therefore all 5 of these conditions are equivalent. And then more to the point, these 2 conditions are equivalent. How we doing? Is everybody okay with that? So we're in business. If you've got some vector field given to you, right, and you're trying to decide, is that or is it not a gradient? Is it or is it not path independent, such as in this example right here? I wanted to know, how do I know this thing's path independent aside from it being given in the statement of the question here? How would I tell? The way you can tell if a vector field is a gradient, aka path independent, compute Green's operator, see if you get 0. It's as simple as that. Very convenient. Okay, now real quick, I want to talk about terminology a little bit. This property of Green's operator being 0 is sometimes called, the vector field is irrotational. I think this is a great term. This is highly descriptive of the property it's being used for. Let me talk you through it. Let's think about Green's operator. What is Green's operator? Circulation density. Right? That was our first point of view on Green's operator. That's telling you, locally in some sense, to what extent is the vector field representing a fluid that has a rotational aspect to it. If I have a body of water here, a little river or something, and the leaf is floating down, it's keeping track of the extent to which the leaf is turning as it rolls downstream. Right? So Green's operator is specifically about the rotational aspect of the vector field. So it being 0 would mean that there is no rotational aspect to the vector field, aka the vector field would be irrotational. You'd think non-rotational, right? But anyway, English is a weird language. Irrotational is the term. So, big fan of that terminology. Very descriptive, very literal. Is everybody with me? Right. Okay, so now, FYI, and this is written down here, but let me point it out. It does say right here, this only works in R2. This is specifically the local test for 2-dimensional vector fields. There is also a local test for 3-dimensional vector fields. Right? So if you're in R3 instead of R2, let's see if I can fit this all on the screen here. Yeah. So instead of testing Green's operator to see if you get 0, you would just test curl and see if you get 0. Now, how do I show this? I claim the proof is practically identical. It's morally equivalent. It's just that it uses a theorem we haven't covered yet. It uses something called Stokes' curl theorem, and we haven't done that yet. So we're going to have to wait until later in Chapter 7. We'll have all those appropriate tools, and what you're going to find is that the argument is exactly this. It's morally identical to what we just did. But we'll fill in those blanks later. For the moment, take it as a given. In 3 dimensions, curl being 0 is the local test. Okay. All right, so quick example. Here is a vector field. Is this vector field a gradient, I ask? All right, well, let's see here. First thing to observe, there are 3 coordinates for this vector field. We're in R3. You can't talk about Green's operator on this vector field. Green's operator is specific to 2 dimensions. Here, the test is curl, right? So I'm going to compute the curl of this thing. At least I'm going to start computing the curl. By the way, make sure you're good with the formula for computing curl. Make sure you're proficient at being able to crank that out. It's going to come up. You know, make sure that you're good with that. The very first thing I write down, first coordinate is this. There is also a second and a third coordinate, but in fact, I don't even have to compute the second and third coordinate. Remember, the only reason I need to understand curl is I simply need to know, is it always exactly 0 or not? And I can already see not. Look, just by looking at the first coordinate. The first coordinate is already not 0. If the first coordinate's not 0, the vector itself is not 0. So game over, we lose. The curl is not 0. And if the curl is not 0, then this is not a gradient. Is that good? Everybody happy with that? Okay. So in a case like this, if you were being asked to do something with this vector field, maybe you're computing a line integral, what have you, don't try to find the anti-gradient. There is none. There's nothing to be found. Don't try to use path independence on this vector field. This vector field is not path independent because it's not a gradient because curl is not 0. So any path independence arguments on this vector field are just nonsense. Right. Okay. All right. Let's see another example. We've studied this vector field previously. Looks kind of like this. It's the stirred pot, right? Back in Chapter 3, we wrote this down. Let's ask the question, is this a gradient? Okay, well, we have 1, 2 coordinates. That means this is a 2-dimensional vector field. The local test for 2-dimensional vector fields is Green's operator. So we compute Green's operator, and check it out, we get not 0. And so therefore this is not a gradient. Again, not a gradient. Everybody buy it? Now what's nice about this example is it comes with some attached geometric satisfaction as follows. Let's think about this vector field just from a geometric point of view. If this were a gradient, let's think about what would happen if I were to start at this point right here and do like that. Well, if it were a gradient, it would have to be path independent. That vector line integral would have to be 0, but it isn't. Because I'm going in the direction of the gradient everywhere along this curve. Right? I can just, piece by piece, notice that every step along the way on this curve, that vector line integral is positive on each little piece. So, just by looking at this vector field, I can see that this closed line integral is not zero. So it can't be path independent. It can't be a gradient. This would be an Escher-Stairs situation. Totally analogous to the Escher-Stairs deal. Is that cool? So good that the test says no, right? I mean, the test says no, much more easily computed with just a little bit of algebra, but it gets an answer that is entirely consistent with what it had. I can see geometrically what the answer had better be. Okay. All right. So, I want to show you what I think is a really nice conceptual tool. This is not in the book. You don't have to use this, but I think that this is really, really helpful to keep track of things. I'm sure you all have noticed there's a bunch of stuff going on in this material, right? We talked about this from the beginning of the course, chapters 6 and 7. There's a lot of stuff, a lot of objects with various relationships and theorems that use them and analogies between them, and well, there's still a lot to keep track of, a lot of ideas. So I think it helps tremendously to have a meaningfully organized system for keeping track of the ideas and the players that are involved in these conversations. So this is it, and let me first of all tell you where this came from. Where did I get this? Well, let's see. Let me start with this part. Where did I get this from? You may recall that I've made some vague references to a more sophisticated take on all this stuff, right? Differential forms. I've made a couple of references so far to differential forms, integrals of differential forms, etc. Well, the thing that you do with differential forms is you create something called a chain complex and something else called a co-chain complex. And suitably defined chain complexes and co-chain complexes allow you to do some sophisticated math with differential forms, and the punchlines are a lot of the theorems that we're talking about here. That we're not going to go into that level of sophistication. So what is it that I've got here highlighted? This is, roughly speaking, this is what chain complexes and co-chain complexes look like. This is the playing field on which the sophisticated arguments about vector calculus get proved. So this, with all the rigor, abstraction boiled out of it, right? You don't need to worry about all the ugliness. But the underlying structure, the naturality of the placement of these things fits together in very meaningfully, very importantly, powerful ways if you lay them out like this. Because again, this is real, right? These are the chain complex and co-chain complex that really do powerful things. Okay, so let me remind you, we talked previously about composing the gradient operator and Green's operator, and that this gives you an exact sequence, by which I mean, recall, if you have a function and you look at its gradient, if you then take that gradient vector field and compute Green's operator, you will get 0. And furthermore, if you start with some vector field and you compute Green's operator and you get 0, that actually means that there must be some function whose gradient is that original vector field. So this works both ways. Every gradient has Green's operator being 0. Every time Green's operator is 0, you have a gradient. Of course, we talked about this theorem just a few minutes ago, right? But this is what it looks like on this diagram. This is the niceness of putting them together in this way is that you can say all that same thing with just the fact that this is an exact sequence. Everything has a lifetime of 2, however you prefer to say it. Okay. Now I'm going to make the innocent observation that something morally equivalent is basically true when you're talking about regions, curves, points, how they're connected by boundaries. And I don't know if you've ever thought about this before. And by the way, I should put in a disclaimer. There is an asterisk on this. There's a couple of little sloppinesses in how I'm going to say this that technically ought to get cleaned up. I'm not going to worry about that in this class. It's not what this class is about. It doesn't affect us. It's all formalities that can all be taken care of. There's no actual problem here. Now, that said, if you take a two-dimensional region and you look at its boundary curve, think about what that boundary curve would look like. I make the observation that boundary curve can't have endpoints. I mean, let's draw the picture. Here's a two-dimensional region. The boundary curve looks like that. The boundary of the boundary is 0. Said differently, it starts and ends at the same point. There is no starting point. There is no sort of actual starting point, actual ending point. So a neat fact. Boundary of a boundary is always 0. Isn't that neat? And then I claim it also goes the other way, and again, asterisk, and forgive me for my sloppiness on this, but again, it doesn't affect us. If you have a curve whose boundary is 0, in other words, if you have a curve that maybe starts at some point, but then after a while it comes back and ends at exactly that same point, then notice that means that it's like you're putting down a fence, and by ending at the same point you've started, you have closed the fence, and that intrinsically makes the fence, the purple curve here, the boundary of a region. Geometrically, you get the same thing. This is how two-dimensional geometry works. It's just, kind of cool. All right. Okay. All right. Here's another really neat thing I'm a big fan of. Here's the fundamental theorem of line integrals. Here is Green's theorem. At a casual glance, these look like very, very different theorems. They appear basically unrelated. One of them is about two-dimensional regions and stuff. And the other one's about a curve and endpoints. One of them's about change. One of them's about circulation. One of them has a Green's operator in it. One of them doesn't and has the gradient operator. They seem like they're completely different, right? Okay, well, keep in mind what we're looking at here and the way this is laid out. We're seeing kind of shadows of much more powerful and sophisticated realities. And here's one that I, again, can't flesh out for you. We just can't do it in Math 219. There is a single theorem for which both of these are a special case. Both of these theorems, completely different looking. They're actually both special cases of the generalized Stokes' theorem, what they call the generalized Stokes' theorem, which is too abstract to state in this course. But as a result of them being special cases of the same theorem, I mean, they're really kind of the same theorem, just in kind of different contexts. They lay out very similarly on the diagram. So here we go. Notice we have in the fundamental theorem of line integrals a gradient. Notice we have in the fundamental theorem of line integrals boundary points. So if you look at both sides of the equation here, what it's saying is here we're taking my initial function and we're looking at the boundary points and evaluating the function at those points. That gives us f of b minus f of a. On the right side, we're taking the gradient vector field. We're doing a line integral over the given curve. And altogether, what it's saying is that when you push to the right on the operators, when you push to the left on boundaries, you get the same thing on either side. Okay, whatever. That's just how the arrows play out. Now let's do the same thing for Green's theorem, though. Green's theorem, we have Green's operator on the right. We have a boundary curve on the left. And if you look at what the left side is, it's a line integral of the original vector field evaluated over that boundary curve. And if you look at the right-hand side, it's a double integral of the Green's operator function on the original two-dimensional region. Said differently, if you push to the right on the operators, you push to the left on the boundaries, you get the same thing. So notice now, diagrammatically, they look exactly the same. In terms of how they lay out on the page, on this diagram, really the same. Right? So I think this is a thing of beauty. In a sense, you don't even have, and you're careful with the diagram, you make sure to be careful with how you write things down. It's like you don't even have to memorize the theorems. All you have to memorize is go to the right there, go to the left here, and same thing on both sides. Same exact thing over here. Right? And I'll share this, for whatever it's worth, in my life, I'm not clear that I have ever memorized these theorems. I memorized the pattern when I was y'all's age. Right? And this diagram is emblazoned on the back of my eyelids, right? I couldn't forget this if I tried. Right? And because I'm very comfortable with the diagram, and the pattern is simple, every time I need one of these theorems, I just think about the diagram. Okay, left, right, okay, boom, theorem. So, I think that's pretty interesting. I hope you'll find that to be useful. Let's see here. How are we doing on time? We are out of time. Okay, so I'm going to have to call it here. Let's see here. I will say a couple more. I'm going to draw the line right here, and I will say a little bit more about this next time, and then we'll have to talk about anti-gradients. Okay, y'all have a good rest of your Wednesday. See you on Friday.